groups and analysis on metric spaces.
Hear me? It's coming through? Okay, well, it's a great pleasure to be here on this occasion for Dennis's birthday. So the theme is pretty much spelled out by my title. But the idea is, the main content is, I'm going to apply analysis to study negatively curved spaces. Okay? So what I'd like to do to kind of set the stage is begin with a result which has inspired an enormous amount of mathematics and is sort of one of the key inspirations for everything I'm going to be talking about here. And then after I sort of discuss this, then I'll indicate where things will go. And so that's Mostow rigidity. And so Mostow proved his rigidity theorem so it's for arbitrary symmetric spaces of non-compact type. But I'm just going to talk about the version for hyperbolic space here. Okay? So I'll say a little bit more about the other rank 1 cases later on. So we're looking at hyperbolic space in dimension at least 3. Okay? And so let's say we have two closed hyperbolic N manifolds. Right? So these are closed manifolds, closed Riemannian manifolds, where the curvature is -1 at every point and at every 2 plane. Okay? So the theorem says that, this is one way of stating the theorem, that if you have two manifolds, if their fundamental groups are isomorphic, well, then they're isometric. So hyperbolic manifolds are completely determined up to isometry by their fundamental groups. So this is kind of an amazing fact the first time you hear it. Now, if you think about a closed hyperbolic manifold, right? So this is a Riemannian manifold, curvature -1. If you pass to the universal cover with the associated metric, then you have a simply connected manifold with curvature -1. And such a manifold is isometric to hyperbolic space. So therefore, this leads to the next version of the theorem. Instead, you think about the universal covers of these manifolds as copies of hyperbolic space. The fundamental groups will be acting there by deck transformations. So these deck transformations are by isometries. And so you have now, if the fundamental groups are the same, you have, say, the same group, let's call it G, acting by isometries on hyperbolic space in 2 different ways, by one deck group action and by another deck group action. So this leads to this version. If you have 2 discrete co-compact isometric actions of some group G on hyperbolic space, well, then they're isometrically conjugate. So discrete just means the actions are properly discontinuous, or equivalently, essentially you get a discrete subgroup of the isometric group of hyperbolic space. Co-compact just means the quotient is compact. And so an isometric conjugacy is just an isometry which is equivariant with respect to the 2 actions. Now, another way of thinking about essentially the same thing is to sort of pass to the ideal boundary of hyperbolic space. So if you think of the Poincare-Ball model for hyperbolic space, then at infinity you have the unit sphere, so Sn -1, and every isometry of hyperbolic space is a diffeomorphism of the open ball, which extends to a diffeomorphism of the closed ball, and the restriction of that to the unit sphere is a Möbius transformation, conformal diffeomorphism. So now you can replace these actions, isometric actions on hyperbolic space, with actions on the sphere by Möbius transformations, by taking each isometry of hyperbolic space and looking at the corresponding Möbius transformation of the sphere. So then it translates to this statement. If you have 2 Möbius actions of the same group G, so the condition that the isometric actions are discrete and co-compact translates to a condition on this, which is easily expressed in terms of the action on triples of points. you look at the space of triples of distinct points in the sphere, and it's not hard to see that the original action is co-compact if and only if the action of the group on that space of triples is co-compact. And discreteness corresponds to proper discontinuity. Okay, so this is going to be kind of the
distinct triples, right?
Distinct, right? Triples of distinct points. Okay, so what does this mean? Well, for one thing, so we're saying that if you have a group G, and it happens to have a discrete co-compact isometric action on the hyperbolic space, then that action is unique up to isometric conjugacy. All right, so we can, most groups won't have such actions, but if you have a group which has one, then it's canonically associated with the group G. There's a unique such action. So in particular, any conjugacy invariant, or isometric conjugacy invariant of that action can be viewed as an invariant of the group itself. Okay? So in particular, if you think about this geometrically, you look at the action of the group on hyperbolic space. An obvious thing to do is to look at the quotient. For instance, if the action is free, then the quotient will be some manifold, hyperbolic manifold, and then you can look at some geometric invariant of that. For instance, the volume. Or you can look at closed geodesics. There'll be infinitely many of them, and you get a set of real numbers, namely the length of the closed geodesics. And all of this structure will be just canonically attached to the group. So now I want to mention a few other corollaries of Mostow rigidity. And these will be properties of, you can view them as properties of the group G, right, which you might think of as a fundamental group of a hyperbolic manifold. Now, the group is just a purely algebraic structure. And these statements are algebraic statements, but proving them by just algebra would be virtually impossible. Okay? So they're statements where you really need something like Mostow rigidity. Some of them you can prove without it, but okay. So let's look at the case where you have an isometric action which is faithful, meaning right. So every element acts non-trivial. So there the group ends up embedded as a subgroup of the isometric group of hyperbolic space. So it's a discrete co-compact subgroup, and then it's not hard to see just from unwinding definitions. If you have an automorphism of the group G, right? So then you can precompose this action of G on hyperbolic space with that automorphism. And that gives you a new action of the group on hyperbolic space. Now, by Mostow rigidity, that's isometrically conjugate to the original action. Okay? And therefore, you can associate that to that automorphism an element of the isometric group of hyperbolic space. Okay? And that will normalize this subgroup G. So the upshot is, what you get is that the automorphism group of G is basically just the normalizer of your group G in the isometric group of hyperbolic space. Okay? And right, so if you're interested in, so this is one way of getting your hands on the automorphism group of G. But if you're interested in, say, the outer automorphism group, so this is another standard group theoretic object. The automorphism group modulo the normal subgroup of inner automorphisms, the ones coming from conjugation, right? And then in this case, what you get is you get the normalizer modulo the original group G. Okay? And since this G is a co-compact subgroup of the isometric group, this is going to be a compact group. And it's not hard to see it's zero-dimensional. So the upshot is that this outer automorphism group is a finite group. So another consequence of Mostow rigidity is this. So if you take, let's say we have again the case where the group is embedded in the isometric group of hyperbolic space, and for simplicity, I'll assume that the group has no torsion. Okay. So then you can look at, you start with your group G, you can look at the ways in which this group can be enlarged to another group so that it sits as a finite index subgroup. Okay? And I'll assume that the enlarged group, so this extension H, is torsion-free as well. All right? So the claim is that there's an upper bound on the index for such an extension. Okay? And the reason this follows from Mostow rigidity is, so it's just a matter of kind of unwinding definitions. So you can get your original group G is sitting inside the isometric group of hyperbolic space. Now you imagine that this G sits as a finite index subgroup of some H. Okay? And so you can use Mostow rigidity to produce an embedding of H into G. Okay? So that the image basically is equivalent to G includes an H, so you have a commutative diagram, and so then you see that H is going to be a discrete co-compact subgroup of the isometric group of hyperbolic space, right? And then you look at the volume of hyperbolic space modulo H, right? So the index tells you, if you know the volume of hyperbolic space modulo G, then the volume of hyperbolic space modulo H will be that divided by the index. Okay? And now, so Margulis, because of the existence of the Margulis constant, you know there's a positive lower bound for the volume of such a quotient. Okay? So this gives you an upper bound on the index. So this is another kind of deep group theoretic consequence that just pops out of Mostow rigidity. Okay, so another property is, there's another thing you can attach to a group, G, which is, I guess I don't want to really dwell on this. So given a group G, you can look at the automorphism group, right, which is the group of isomorphisms from the group to itself. But you can also look at the commensurator, which is an object which corresponds to looking at isomorphisms between finite index subgroups of the group. So you take two different finite index subgroups, you choose an isomorphism from one to the other, okay? And you can get a group by basically declaring two such guys to be equivalent if they agree on a finite index subgroup, okay? So this gives you an abstract group attached to any group G, and again, by applying Mostow rigidity, this commensurator sits inside the commensurator. I mean, it can be viewed as a subgroup of the isometric group itself. Every abstract commensuration is realized uniquely by conjugation by some element of isom HN. Okay. Anyway, so these are facts that are sort of very fundamental from a group theoretic point of view.
How do you use torsion-free to get that invented?
Oh, I didn't. I was just using torsion-free to avoid sort of idiotic examples where you take the product with a finite group. So I mean, you can formulate a version of this statement allowing torsion, but I didn't.
How do you get that arrow?
So if it's torsion-free, okay. So to get the arrow, so you look at H acting on G by conjugation. Since G has finite index, they're finitely made conjugates. The intersection will have finite index in G. And now H will embed in the automorphism group of that finite index subgroup. Okay. Okay, so let me shift gears a little bit. Now let's look at the point of view of geometric group theory. So I don't want to be dogmatic about this, but sort of one way of thinking about geometric group theory is that you try to understand groups by using metric geometry.
You use torsion-free because when you conjugate, it might commute. Then we have finite order. It wouldn't be embedding. It wouldn't be embedding.
Right.
Okay.
Right. I mean, that's why. Yeah. So I mean, you can formulate a version where you allow torsion, but you have to exclude. You have to say something that centralizes. So. Okay. So let me just recall this. So let's say you have a finitely generated group G. All right. Take a generating set, sigma. So I'll assume that it's symmetric. So if it contains an element, it contains the inverse. And now from this data, you build a Cayley graph, right? So gamma's Cayley graph with respect to sigma. So that just has a graph of the vertex set G, where you join two vertices or two group elements by an edge, if and only if one is equal to the other right multiplied by some generator sigma. So let's give this a path metric where edges have length 1. So this is a connected graph. This follows from the fact that this is a generating set. And so now you have a nice metric space. The left translation by group elements in G induces a graph isomorphism of the Cayley graph. So it gives you an isometric action of your group G on the Cayley graph. And so in this way, we've associated a metric space with a group. Now, there are lots of metric spaces that will get this way. If you change generating sets, you will get a new Cayley graph. But the point is, the metric geometry in the coarse sense is the same for all Cayley graphs. And formally, the property that they have in common is that they're quasi-isometric. So, what's a quasi-isometry? So it's just a map between metric spaces of quasi-isometry. If you have two constants, so I think of use an L here for a bi-Lipschitz constant, or Lipschitz. A is the additive constant. And so the conditions are, given 2 points in the domain, if you look at their F images, f of x1, f of x2, then that's controlled by linear functions from above and below. Okay? And so if L is 1 and A is 0, this is saying that this is an isometry. Okay? And the second condition is that every point in the target space lies within some uniform distance A of the image of the map F. So the map is almost surjective to within error A. Okay, so the point is that we can associate a quasi-isometry class of metric spaces with any finitely generated group, right? Namely, we get the quasi-isometry class of any Cayley graph, so Cayley graph for any finite generating set. So in fact, there are many more metric spaces. So there's what I call the fundamental lemma of geometric group theory, which just says that if you have a geodesic space, so proper just means closed balls are compact. And then you have a group acting on it, say G, which is discrete, co-compact, and isometric, then the group is quasi-isometric to X. In other words, so I guess here I need to say, so these conditions imply that G is finitely generated. And then you take any finite generating set for G, and you look at the associated Cayley graph, and that will be quasi-isometric to the space X. All right? So this gives you lots of other spaces which are quasi-isometric to the group. And coming back to the setting of Mostow rigidity, if you have a group which happens to admit a discrete co-compact action on hyperbolic space, then by this lemma, you know that it's quasi-isometric to hyperbolic space. And Mostow says that this particular action gives you a sort of a canonical object, in this quasi-isometry class. Okay. So there's another, so I guess another issue that comes up in geometric group theory, and which has received a lot of attention, is the problem of classifying finitely generated groups up to quasi-isometry. So you want to, given two finitely generated groups, you'd like to know if they're quasi-isometric. Given one finitely generated group, you'd like to have a nice description of all the groups which are quasi-isometric to it. And so, there's a beautiful variant of Mostow rigidity that's due to Sullivan, Gromov, Tukia, and I guess in this particular form, maybe Kennan and Swenson. which says this, that if you have a finitely generated group and it's quasi-isometric to hyperbolic space, meaning that some Cayley graph is quasi-isometric to hyperbolic space, well then, in fact, there is a discrete co-compact isometric action of this group on hyperbolic space. So it's essentially the converse that I just pointed out. If you have such an action, then by this fundamental lemma, the group is quasi-isometric to hyperbolic space. So this gives a complete, well, it gives a very satisfactory description of the. I think a little bit later, the ingredients will come up. It's basically your theorem about uniformly quasi-conformal groups, maybe in disguise. Okay. So, right. So this has a nice, this nice picture that if you take, right. So you take a discrete co-compact subgroup of the isometry group of hyperbolic space, then somehow you have this nice kind of canonical overgroup or supergroup, the full isometry group, right? And that larger group, the Lie group, contains anything quasi-isometric to the original group. Okay. Whereas, I mean, you can take, dimension 3. There are lots of co-compact, discrete co-compact subgroups of the isometry group of hyperbolic space, and from an algebraic point of view, they can look rather different from one another. There are many families of commensurable subgroups, but there are many incommensurable families, and yet they all sit inside the same Lie group, the isometry group Hn. So, okay, so let me shift gears a little bit. So I want to now look at the quasi-conformal analysis or geometry, which is the technical framework that's used in the proof of Mostow rigidity. Okay, so I mean there are other proofs which sort of which avoid at least part of this, but those proofs do not generalize very well. In particular, you can't. The only proof I know of this theorem right here is essentially the original one, which relies on the quasi-conformal analysis. Okay, so let me recall the definition of a quasi-conformal homeomorphism. So you take a map between, say, homeo between two metric spaces. So then you can define this quantity for every ball. So this is just saying you take a point in the domain, you look at the R ball, and then you apply the map F to it. Right, so you get some subset. Here's F of P. And then the image of the ball has an in radius, and it has a circumradius. Right, and then you can look at the ratio of the circumradius to the in radius. And that's basically what this is. Okay, so it's this quantity is a measure of the eccentricity of the image of the ball, measured at the center F of P. Okay, and so the map is quasi-conformal if there's some number h, so that this quantity lim sup for each fixed p, the lim sup as r goes to 0 of this quantity is less than h. Okay, so every point in the domain, if you look at asymptotically at small balls, their images look like sets with controlled eccentricity. Okay. Now, so these were studied classically, I guess, the Teichmuller and Alfors, well, many people. But I'm going to give sort of a quick recap of just a few facts about quasi-conformal homeomorphisms. And of course, there's a long story. And what I'm going to be doing is kind of picking out those things which have been, well, first of all, those things which appear in the proof of Mostow rigidity and variance of it. And also, these are the properties which are going to generalize to the setting that I'll be discussing later. Okay, so I'm omitting a huge amount of stuff here. So first of all, if you have a quasi-isometry from hyperbolic space to itself, then, so again, you have the Poincare ball model for hyperbolic space. Right? So if you have a quasi-isometry of hyperbolic n+1 space to itself, then, so that's a self-map of the open ball. And so the assertion is that this extends in a canonical way to a map from the closed ball to itself. Okay? Now, the quasi-isometry doesn't have to be continuous, right? But what you find is that if you take any point on the unit sphere, then that is a point of, that's a continuity point of the map, which is defined on the open ball. And therefore, there's a unique extension to the boundary, which is a continuous map of the sphere to itself. And that's a homeomorphism. Okay? So the connection with quasiconformal is that it's every homeomorphism that you get that way is actually quasiconformal. Now, compositions and inverses of quasiconformal homeomorphisms are also quasiconformal. So getting compositions to be quasiconformal is more or less trivial. Proving the inverses are quasiconformal is a very substantial, it's a substantial result. Classical, but substantial result. Another fact is not at all obvious from the definition that these homeomorphisms belong to some Sobolev space, some Sobolev regularity. And they're absolutely continuous with respect to Lebesgue. So the image of a set has measure 0 and only if its image has measure 0 under the homeom. Okay. And the same thing holds along lines. So it's quasi-conformal homeomorphisms are ACL. I mean, this is, of course, related to the Sobolev condition here. But it says, so for almost every line, for instance, if you look at lines parallel to coordinate direction, then for almost every line, if you restrict your homeo to the line, so you get a map from the line or its intersection with the domain, with the line, into this other domain, and this is absolutely continuous with respect to one-dimensional Hausdorff measure. Okay, meaning if you take inside this line, you take a set with one-dimensional Hausdorff measure 0, it gets mapped to something with one-dimensional Hausdorff measure 0. Okay.
Even though the line itself, image line, could have bigger Hausdorff dimension.
Well, for almost every, it can in general, but for almost every.
For these lines, it would not.
Straight lines.
Yeah, these are straight lines.
It's the big measure from the left. From the measure.
It's one-dimensional Hausdorff measure on the line.
Right. Also, these lines that get converted into fractal lines are special for anything in the family. I don't understand the meaning of the statement. So the image line has what structure?
It's really, think of it as a statement about the map restricted to the line. So it will, right? It will map sets of, it will map sets of.
It'll map sets of one Hausdorff measure 0 to one Hausdorff measure 0. Right. You're not saying about the structure of the image line.
Let's see. So the map, it will, for almost every line, the map will be Sobolev. It's going to be in W1N for the line. Okay, so then, of course, this is leading up to this fact, which is kind of also very surprising for people who don't think about sublove mapping. So the quasi-conformal homeomorphism is differentiable almost everywhere. And in fact, this seems like a minor point at first sight, but it's not just differentiable almost everywhere, but the derivative is non-singular almost everywhere. Okay? So now there are other properties that show up. So this one doesn't actually appear in Mostow rigidity, but it's an important thing, important fact. So if you have a sequence, so let's say they're defined on the entire sphere, you have a sequence of uniformly quasi-conformal homeomorphisms, meaning that this number h, you can use the same number h, this eccentricity bound, for all the homeomorphisms. So then, and there's a subsequence which either converges uniformly to a quasi-conformal homeomorphism, or the subsequence will converge uniformly to a constant map in compact subsets of the complement of a point. Okay, so it's converging to a constant away from a point. And then the Liouville theorem, if you have a quasi-conformal homeomorphism, whose derivative is conformal for almost every point, well, then it's a Möbius transformation. In other words, it arises it arises from an isometry of hyperbolic n+1 space, and you extend it to the boundary. Okay. So now finally, there's uniformization. So if you have suppose you have a measurable Riemannian metric on the two-sphere, which is bounded, meaning that this metric is less than there's some fixed constant c, so it's less than, it should be a g0 here. So it's less than c times g0 and bigger than 1 over c times g0. g0 is the standard metric on the two-sphere. Well, then such a metric is conformally equivalent to the standard metric. Okay? But here, so this sounds like just the classical uniformization theorem. The difference is that the conformal equivalence is coming from a quasi-conformal homeomorphism, whereas in the classical case, you'd have a smooth Riemannian metric, and the conformal equivalence will be a diffeomorphism. Okay? So formally, we're saying there's a quasi-conformal homeomorphism such that the derivative, which is a map from the tangent space at this point to the tangent space at the image, this map between tangent spaces is a conformal linear transformation between this inner product space and that inner product space for almost every x. Okay?
So since you only care about conformal equivalence, you only care about G up to conformal equivalence to begin with.
Right.
So those bounds just mean something else, right? You don't care about the scale.
Right. It's just a compact way of staying. Yeah. Right. Okay. So now let's just see how these ingredients come together in the proof of Mostow rigidity. So let's come back to this situation. We have two discrete co-compact isometric actions, right, by the same group. And the goal is to show that they're isometrically conjugate. So the first step is, let's just recall. So then you have the associated Möbius actions you get from replacing every isometry of hyperbolic space with the associated Möbius transformation of the sphere. So step one, there's a quasi-isometry from hyperbolic space to itself, which is equivariant with respect to these G actions. So this is basically just the fundamental lemma of geometric group theory, because you have the same group G. It has a discrete co-compact isometric action here, but the fundamental lemma tells you that G is quasi-isometric to Hn. And likewise here, if you just inspect the proof, then if you can sort of compose one quasi-isometry with the inverse of the other, and you get this quasi-isometry from Hn to Hn, which will be equivariant. Okay? So So you have this quasi-isometry. Now you apply this first fact that I mentioned on the list of properties of quasi-conformal homeomorphisms. So you have a quasi-isometry from hyperbolic space to itself. And so this gives rise to a homeomorphism from the sphere to itself, which is quasi-conformal. Okay? And the equivariance property is inherited from the original the equivariance property of F. So you have now a quasi-conformal homeomorphism from this sphere to that sphere, which is equivariant with respect to the one action here and the two action there. Okay. So now the goal is to show that this is actually conformal, or Möbius transformation. So so suppose that the derivative of this quasi-conformal homeomorphism, so that the derivative exists almost everywhere and is non-zero almost everywhere. Suppose it's not conformal almost everywhere. Right? So that means there's a positive measure set of points where it's not conformal. Right? And so so then you look at the set where the derivative is defined and not conformal. So if you have you have such a point, you have a linear the derivative maps the tangent space at that point to the tangent space at the target. You have inner products in the domain and target, and it's not conformal. So that tells you that there will be a subspace corresponding to the directions which are stretched the most, right? Being conformal means that all directions are stretched by the same factor. If it's not conformal, there will be subspace, non-trivial subspace, which is of guys which are stretched the most. And by the measurability of this derivative, what you get is that you get a measurable subbundle of the tangent bundle here. And then from the construction, you see that the subbundle will be invariant under the one Möbius action here. Okay? If you apply a group element on the domains to the domain sphere using the equivariance, you just and this construction of this maximal stretch direction, you see that the subbundle will be invariant. Okay? So we have now a G-invariant subbundle. That should be a little bit sloppy because a priori the dimension of this subbundle could be fluctuating. It could be, K in one place and L somewhere else. But let's say, let's take a point of approximate continuity of this subbundle. So that means it's a point in the sphere, the property that if you look at the subbundle at that point, so that's subspace of the tangent space at that point, right? And now you look at smaller and smaller balls centered at that point, and you look at inside the ball, you look at the subbundle, and you look at the set of points where the subbundle is, say, epsilon close to its value at the center. Okay? So that set of points will have density approaching 1 as the radius goes to 0. Okay? So maybe just to get the idea here, just suppose, and this is, of course, more than you can suppose, but suppose this happened to be a continuity point of the subbundle. You're just lucky enough to have a point where the subbundle is continuous. And now let's think about the effect of the dynamics, right? So the group preserves the subbundle, and then you think about how these Möbius transformations act if you have an element which is sort of strongly expanding, so it's with north-south dynamics, then you will expand that region where the subbundle has constant coefficients so that it sort of stretches all the way around the sphere. Okay? So if you trace this through, what you conclude is that in some upper half space model for hyperbolic space, i.e. you can find some point in the sphere, okay? So then the complement of that point, that's a copy of Rn minus 1. And what you see in that Rn minus 1 is a constant coefficient subbundle. Okay? So this measurable subbundle then will extend to a smooth subbundle, except at one point. And now you observe that you look at how this group is acting. It's acting by Möbius transformations, which are smooth, right? And it's preserving this subbundle, which, well, which extends smoothly except at a single point. You check that means that the set of points where it doesn't extend smoothly must actually be fixed by the group. So the group must actually fix this sort of singular point, all right? And this is a contradiction by sort of that would say the group acts parabolically, which is impossible. Okay, so the upshot of this is that the derivative must be conformal almost everywhere, and then you apply the alluvial theorem, which I mentioned earlier. It tells you the derivative is conformal almost everywhere. So actually, this is a Möbius transformation, and so therefore it's equal to the boundary homeomorphism for some isometry, unique isometry, say f bar. And then that so this thing is equivariant with respect to the two Möbius actions. You just chase through and you see that means this f bar is equivariant, and you're done. Okay. So so the question is, so this is sort of motivating the rest of the discussion. So we'd like to extend the rigidity theorem, these two rigidity theorems here, and get, for instance, the corollaries that I discussed. And to do that, it's going to be necessary to develop the quasiconformal theory that went into it. So the motivation, well, as I said before, Mostow rigidity tells you that at least for certain groups, you get a canonical geometry associated with the group. You have a finitely generated group. It always comes with this quasi-isometry class of metric spaces. And you can ask if there's a canonical geometry in there that can be attached to the group. And it's sort of a geometrization problem for in a group theory world. And this is basically the strategy that's been used repeatedly to prove rigidity theorems. And so I just want to comment that they're away from the world of negative curvature. There are other structures that have been very useful for proving rigidity theorems. So you can use topology or coarse versions of topology, or asymptotic cones, or differentiation, coarse differentiation. But when you're looking in the negatively curved setting, at least sort of in many cases, the only known approach, the only known framework for addressing rigidity problems is using this kind of analysis. Okay. So that's the motivation coming from group theory. But just from the point of view of analysis, it's simply a fascinating question to see to what extent one can extend this analytic theory beyond the setting of domains in sphere. Okay. So what I'm going to do next is talk about hyperbolic spaces, or Gromov, so it should be Gromov hyperbolic spaces and groups. So these will provide kind of the setting to which we'd like to generalize this whole story. And then I want to talk about the quasi-conformal analysis in metric space setting. So what are Gromov hyperbolic spaces? So here, Gromov geodesic metric space is hyperbolic if geodesic triangles are delta thin for some fixed delta. So this just means that you have a geodesic triangle. It's delta thin if, when you pick a point on one of the three sides, well, then there's a point on one of the other two sides, let's say here, so that this distance is less than delta. Okay? And so some examples, first of all, hyperbolic space. So this follows, the geodesic triangle lies inside a copy of the hyperbolic plane, and then this follows from Gauss-Bonnet that geodesic triangles have in radius, which isn't very big, just by looking at Gauss-Bonnet. The area is less than pi. So if you have a complete simply connected Riemannian manifold with uniformly negative curvature, then it's also hyperbolic. And the reason is there's a comparison theorem due to, I think, probably Courant, which tells you that that if you have a geodesic triangle inside such a manifold, so let's say that the curvature is less than or equal to -1, which you can arrange by rescaling if you want, under the assumption that the sectional curvature is uniformly negative. So then there's a theorem that says that geodesic triangles in such manifolds, so if you take some, say, p x, y, so here you have something whose curvature is less than or equal to -1, then you can compare the geodesic triangle with a geodesic triangle in the hyperbolic plane. Okay, so here's a geodesic triangle where the corresponding sides have the same length. Okay, and the comparison theorem says that if you choose a pair of points, let's say a point here and a point there, you construct the corresponding points on this triangle, which is sitting in the hyperbolic plane. So let's say this distance is the same as this one, right? This distance is the same as this. So then you can compare the distance between the 2 points on the geodesic triangle here with the 2 points in the geodesic triangle here. And then, so here's the length, say, L hat, and here's L. So L is less than or equal to L hat. Okay, so the negative curvature, having an upper, saying something has curvature less than or equal to -1, says geodesic triangles are at least as thin as the geodesic triangles in hyperbolic plane. And so then this gives you the thin triangles property. So an example that I want to come back to is complex hyperbolic space. So this has the I'm not going to define this, but so it's a Riemannian, simply connected Riemannian manifold with a certain normalization. The curvature ranges between -1 and -4, and so it has its own ball model. But this is a complex manifold. If you take a geodesic, take a look at the tangent vector. It's a complex manifold, so there's a complex multiplication. You apply it to the tangent vector, you get an orthogonal vector. And this 2-plane is tangent to an isometric copy of the hyperbolic plane with curvature -4. On the other hand, if you take a vector which is orthogonal to that 2-plane, and you look at the span of that with the tangent vector to the geodesic, so this is a totally real 2-plane, then that will be tangent to a hyperbolic plane with curvature -1. Okay? So this has somehow a mixture of curvature between -1 and -4. So I'll say more about this in a few minutes. Now, you can also just look at convex sets. So in hyperbolic space, you can look at, say, convex subsets of the ball, or look at convex co-compact groups of hyperbolic space and get interesting examples. Another example to consider would be trees, so say simplicial trees. For instance, take a simplicial tree where all edges are equal to 1, have length equal to 1. And you can get other kind of singular examples. You can produce zillions of examples by taking piecewise hyperbolic objects. So here, we'll take a 2-complex, for instance, built out of hyperbolic polygons, okay, glued together by isometries along the edges. And if you have such a complex, that will be Gromov hyperbolic, provided the links satisfy a geometric condition, which is simply that. So if you look at the link, so a link at a vertex, you see a bunch of these polygons. They will have corners arriving at that vertex, and so each such corner gives rise to an arc, whose length is equal to the angle. So it gives you the metric link at that vertex, and then the condition is that that metric length, which is just a finite graph, that should have no closed geodesics of length less than 2 pi. Okay? So I'll discuss some examples of this later. So I started at 320. Okay. Right. So the reason that this Gromov hyperbolic spaces are important is that they're basically a substitute for negative curvature, which is quasi-isometry invariant. Okay. So let me just recall this. So suppose you have a map between metric spaces. It's a quasi-isometric embedding. If this condition holds, this is exactly what I had written down before when I was talking about quasi-isometries. It was the first of the 2 conditions. Okay? So it's the difference between a quasi-isometric embedding and a quasi-isometry is that we don't have the second condition, which is that it's almost surjective. And so quasi-geodesic is a quasi-isometric embedding where the domain is an interval or array or all of R. Okay? So the Morse lemma says that if you have an LA quasi-geodesic inside a delta hyperbolic space X, right? And then if you take gamma bar, this will be a geodesic with the same endpoints. Well, then the Hausdorff distance between the quasi-geodesic and the geodesic gamma bar, or rather the images, is less than this number d. Okay? So we're saying you have a delta hyperbolic space X, you have a quasi-geodesic, gamma, and then you look at a geodesic with the same endpoints, then these 2 subsets have uniformly bounded Hausdorff distance d. Depends only on the the constants LA and the hyperbolicity constant d. All right? So, yeah. And so you have a similar statement where you replace an interval, a finite interval here with the ray, or you replace it with all of R. So for instance, if you have a quasi-geodesic where the domain is the non-negative reals, then there will be a geodesic with the same initial point, so that the geodesic and the quasi-geodesic ray have the same Hausdorff distance d from one another.
I'm sorry, where's delta in this?
That was X is a delta hyperbolic metric space. Yeah, sorry. Okay. So the reason I'm mentioning this, the reason I was talking about quasi-geodesics, is that this Morse lemma implies that hyperbolicity is a quasi-isometry invariant. Okay? So if you take 2 metric spaces, 2 geodesic metric spaces, and they're quasi-isometric, then one of them is hyperbolic if and only if the other is. And the reason this follows from the Morse lemma is you just take your, so you have a quasi-isometry here. You take a geodesic triangle. You apply the quasi-isometry to it. Each of these geodesics becomes a quasi-geodesic. Okay. Now, by the Morse lemma, these will be approximated to within uniform Hausdorff error by geodesics. Okay. Now you apply the thin triangle, so you assume that this guy is a delta hyperbolic. Okay. So you can apply the thin triangle condition over here. So we start with the point here. We'd like to find a point on one of these 2 sides, so we map it over. This will be within uniform distance of some point on this geodesic. That will lie within some distance, say, delta of a point here. That on the geodesic, then you jump to this guy, again, using the Hausdorff error, and then you pull it back and use the quasi-isometry property, and you get that this guy's thin. Okay? So this is the main reason why people talk about hyperbolicity as opposed to a curvature condition, because curvature conditions just are not quasi-isometry invariant. So In particular, because of this, if you have a finitely generated group, it makes sense to say that it's hyperbolic, because one Cayley graph will be hyperbolic if and only if every Cayley graph is hyperbolic. Okay.
Is X assumed to be proper on this slide?
Right here?
For both the Moss and the is this true for just any complete geodesic metric space?
Yes, I mean yeah. So I mean you have to be a bit careful. I mean there are versions of this where you don't even require it to be geodesic and it's sort of, but yeah, I mean if you assume that it's complete in geodesic. Okay, so now a fact that that I want to use, which is sort of, it's not an essential fact, but it's sort of very, very handy psychologically, is that is a statement that any Gromov hyperbolic space is approximable by trees. Okay, so this says the following. So let's take some delta, which is going to be a hyperbolicity constant, n. So then there's some constant a, so that if you have a delta hyperbolic space, so geodesic metric space where triangles are delta thin, you have an n tuple of points, y1 through yn. Well then, so that's this finite subset sitting in X, then you can find a simplicial tree, T, okay, a metric simplicial tree, right? So we're the path metric on the simplicial tree. And you can find a map of that tree into X, which is a 1A quasi-isometric embedding. Okay? So without going back to that slide to remind you what that means, 1A quasi-isometric embedding is just a map which distorts distances by additive error, A. Okay? So just, you can find a tree, you can, which, yeah, I should have said, I'm missing the most important point here, that the image of this map contains the set Y. Okay. So basically, right. So we're saying that the distances between the points in this n tuple are the same to within error A as some tuple in a tree. Okay. And furthermore, the image is what's called A quasi-convex, which just means that if you take any 2 points in the image, you take a geodesic between them, well, then that geodesic will lie in the A neighborhood, the metric A neighborhood around the image. Okay? So because of this fact, if you want to think about tuples, tuples of points in a hyperbolic space with a fixed cardinality, like typically 3, 4, 5, something like that, up to uniform error, you can think of them as just points in a tree. Okay? So, okay, so now I think maybe I'll stop here because I think we're entering new territory.
Are there any questions? Okay, well then let's thank our speaker again.